This is problem 676. It's on page 279. An aluminum pan has a flat bottom whose diameter is as given and a thickness as given. Heat is transferred steadily to boiling water in the pan through its bottom at a rate of 500 watts. If the inner surface of the bottom of the pan is 105 degrees, determine the temperature of the outer surface of the bottom of the pan and the rate of entropy generation within the bottom of the pan in watts per Kelvin. All right, so this is problem 76. Let me make a sketch again. We know, in fact, let me call this section 2 and call this section 1. Okay, so there are two cross sections. The thermal conductivity K of the pan material is given as 237, not 237 watts per meter per Kelvin. And the temperature on the inside of the pan is 105 degrees Celsius. The heat transfer rate, Q dot 1, is 500 watts. And so, since energy is not created or destroyed, then Q dot 2 should be 500 watts as well. Now, the other thing to note, they want us to find the temperature here, T1, but they want us to find the rate of entropy generation. In other words, there should be entropy because there's heat flow, right? And heat carries entropy with it. So there should be an entropy flow rate across section 1 and an entropy flow rate across section 2. Now, do you think that the heat transfer that's occurring is a reversible or irreversible process?
Irreversible.
Irreversible. Heat transfer is always irreversible. So do you think that there's entropy being generated in that process? Sure. Okay. So is the entropy flow rate across section 2 more than or less than or the same as the entropy flow rate across section 1?
We don't know.
Well, it would have to be more, because if entropy is generated, all right, and these are the only two entropy flows we see, well then there would have to be some entropy generation. Because the entropy has to go somewhere. It has to be put into some matter somewhere. And so since the heat is carrying the entropy into the water, and we know entropy is being generated, well then the water must be the thing that has more entropy put into it than the entropy that was transferred with the heat initially. Does that make sense, sort of? Okay. All right, now the other thing that was given is that the diameter of this pan is 0.2 meters. Okay. All right, so let's start off with the temperature at the bottom side of the pan. Now, I'll give you a hint. This pan is in contact with the burner. Would you expect its temperature to be very high or fairly close to 105?
Fairly close.
Fairly close. I agree with you. Why?
It's pretty thin.
It's pretty thin. Also, this is a fairly conductive material, right? So we could simply use, for part A, we could simply use Fourier's rate equation, Q dot equals negative K A delta T over delta X, to ask the question, how much difference in temperature is there? Well, it's negative Q dot delta X over KA or AK, however you want to say it, KA, right? So T2 less T1, in fact, let's write it this way. Let's just go ahead and solve that this is T2 less T1 if this is X2 less X1. So I'll just solve for T1 algebraically so we can save some time and some steps. T1 is T2 plus Q dot X2 less X1 over KA. Now, I haven't defined X yet, but remember that the heat transfer direction automatically defines the direction of X, okay? We always take the positive X coordinate in the same direction as the heat transfer. Otherwise, we don't need this negative sign here. If we take them opposite, then we don't need that negative sign, okay? So X2 is really just the distance. If we make our reference down here, then X2 is the non-zero term, and X1, since that's the reference, is the zero term. Okay. Now, notice that the area can be written as, well, in terms of the diameter. Now, this is really just the thickness, and I just realized I neglected to write down the thickness. The thickness was, let's just put it here, X2 equals 0.04, 004, 1, 2, 3, yeah, meters. Okay, so then K, but we can write A as pi d squared over 4. And see, all we'd really do then is pull the 4 up here, and we'd have it. Okay, so plugging in the numbers, 105, degrees Celsius, plus the 4, well, let's do it in order. Q dot 500 watts times 0.004 meters for X2 times 4 divided by K, 237 watts per meter per Kelvin, divided by pi, divided by D, 0.2 meters squared. What kind of units will we get? Let's see. Watts go away. This would be meters squared, and this is meters squared, so the meters all go away. And we're just left with Kelvin. Question?
I was making sure what's meters for.
Yeah, it's not meters to the 4th, that's 4 times. That's the multiplier at the end.
Okay.
Yeah, good question. It came from the pi over 4 from the area calculation. Anyway, if you plug all of this into your calculator, you find this is about 105.269 degrees Celsius. You were right. Right? The temperature at the bottom of the pan, even though it's in contact with a flame potentially, is not at much higher temperature than the inside. Now, I saw a video of this. I got to try this someday, but I believe it works. You know, you end up on YouTube and you don't know how you got there. Right? But you're there and you're watching this video. Well, this guy took a paper sack of all things. Right? He's out in the woods, took a paper sack and rubbed the inside of the sack with bacon grease. Okay, so he had bacon, so he just rubbed the bacon on it. I don't remember if he rubbed the outside. I think he may have, but basically he just saturated the bottom of the paper bag with bacon grease. Then he took an egg or two and he just cracked them open right inside of the paper bag, threw the bacon in, wrapped the top like it's a little brown paper lunch sack, rolled the top over, put it on a stick and put it right on top of the fire. Basically just held it on top of the flame. The paper bag did not burn. In fact, his breakfast was cooked. The egg and the bacon was cooked. He just took it off and ate it. And you might wonder, how is that possible? Well, the egg and even the bacon have a significant amount of water in them. And the water is in the liquid phase. And until all that water boils off into the vapor phase, the temperature of the food is going to be clamped to 100 degrees Celsius, right? It can't go any higher. And that keeps the temperature. Now remember, the paper bag is extremely thin. So that forces the temperature on the bottom. Even though a flame is impinging on it, it forces the temperature to remain low enough that it doesn't burn. Which is really surprising. You would think a bacon grease soaked paper bag would simply burn, right? But it doesn't. So I've got to try that someday because that was just too neat. But anyway, someday my daughter's going to say, "Daddy, what are you doing?" "I'm cooking breakfast." "You're going to burn it." We'll see, maybe. So now we've got the temperature on this side, 105.269 degrees Celsius or so. All right, now we're supposed to calculate the entropy generation rate. Now, the way I've written this, you'll notice that the entropy flow rate here plus the entropy generation rate should be equal to the entropy flow rate in state 2. Writing that out mathematically would look like this. And so the entropy generation rate should be the entropy flow rate out less the entropy flow rate in, which just makes sense, right? You've got 7 GPM for a flow rate here. I understand these are not GPMs, but I'm using an analogy. And 5 GPM here, then you must have 2 GPM adding to it, all right? So it's simple. Now, notice one other thing. The temperature of these sections, of section 1 and section 2, are both constants. And so if we want to know the flow rate of entropy across section 1, it would simply be the flow rate of heat at the temperature that the heat flows. Okay, remember that from the slides? We haven't really hit on that equation a whole lot. It's in the back of chapter 6. You may want to highlight it. So all we have to do to calculate that entropy, oh, and by the way, S dot 2 would be the same, right? It would be Q dot over T2. Okay? And so this entropy generation rate then would simply be Q dot 2 over T2 less Q dot 1 over T1. But I forgot my 1 and my 2 here. But the heat flow rate across section 1 equals the heat flow rate across section 2. So, let's continue this. So 500 watts, now we have to be careful, we have to divide by T2, and since T2 is so close to T1, this is the one time in the course when I'm going to add not just 273, but 273.15 to get Kelvin. The reason I did that is because the 105 is so close to 105.269, so I felt a need for a bit more precision in the conversion. Okay. So minus for the second term, Q dot 1, which is 500 watts, divided by T1. T1 is 105.269 plus 273.15. We'll have Kelvin. Plug all this in your calculator and you find that the rate of entropy generation, S dot gen, is about 9.39 times 10 to the negative fourth watts per Kelvin. Now, I understand that you don't have a real good feel for entropy or entropy flow rates. I don't either. We can't see them. But you do appreciate the fact that this is a pretty small number. Okay, why does it make sense that this is not an extremely irreversible process? That's what the small number says, right? There's not a high entropy generation rate. So this is not extremely irreversible. It is irreversible, but it's not extremely irreversible. Why is that?
Because you're going through a solid and then into a liquid. And so there's less places for all the molecules to be because they're all kind of, they're bound.
Not really.
No? Oh, okay.
Good guess. It's because these temperatures are so close. There hasn't been much of a change in temperature. The temperature differential is very, very small. Okay? So if you have a substance that cools from 100 degrees down to 20 degrees, that's a bigger change, that's a bigger entropy generation than cooling from 20.5 degrees down to 20 degrees. Make sense? So that's why the entropy generation rate is so small. Any questions?